Jain to all. Today I am here to present the video lecture on the series Control System BEC 602, and topic of my lecture is Root Locus. I am Dr. Amit Garg, Associate Professor in EC Department of AKTU, and so Root Locus is basically a time domain method for determining the relative stability of a open loop control of a closed loop control system. So we will see the introduction. Stability of any closed loop system depends on the location of the roots of the characteristic equation, that is the location of closed loop poles. So we can define the stability based on the location of the poles. So it is advantageous to know how the closed loop poles move in the S-plane if some parameters of the system are varied. Means if in a system, if it will vary some parameter, so what happened, the poles will move. Okay, so the movement of poles, if we will trace the movement of poles by varying any parameter, so the locus that we obtained is called the root locus. So the knowledge of such movement of the closed loop poles with small changes in the parameter of system generally helps in design of any closed loop system. Such movement of poles can be known by the root locus method introduced by W.R. Evans. So this is a graphical method in which movement of poles in the S-plane is sketched when a particular parameter of system is varied from 0 to infinity, and the parameter that we are choosing as per our curriculum is basically the gain, open loop gain. So we will change the open loop gain, and we will draw the locus of roots, movement of roots. Okay, so here in this case usually the parameter is gain, but any other parameter may be varied. But for root locus method, gain is assumed to a parameter which is to be varied from 0 to infinity. Okay, we can also vary the gain from minus infinity to 0, but that is the part of inverse root locus. So right now we are focusing only on the root locus. Okay, so parameter will be varied from 0 to infinity. So we will see by numerical that how we'll draw the root locus. Okay, so consider unity feedback system for which open loop transfer function is given as k by s obtains root locus. So we will write the characteristic equation. Characteristic equation is 1 plus GHHS equals to 0. HS is 1. So this comes out to be s plus k equals to 0. So this is a very simple question. We can see s is directly equal to minus k. Now we will vary the value of k. We will make a table. We will vary the value of k and obtain the value of s. So we will vary the value of k from 0 to infinity. So we will take the value 0, 1, 10 up to so and infinity. So we can see the values for k equals to 0, s equals to 0, for 1 minus 1, for 10 minus 10, and like this minus infinity. Then we will plot it in S-plane, real part and imaginary part. So for s equals to 0, k equals to 0. For s equals to 1, k equals to, for k equals to 1, s equals to minus 1. For k equals to 10, s equals to minus 10, and for k equals to plus infinity, s equals to minus infinity. It means you can see the root locus for this case is entire negative real axis. Okay, so this is the simple example. So this is the root locus. Now we will see another problem. We can see here k times s plus 1 upon s times s plus 5. So in this particular question we have added one pole and one zero, and we'll draw the root locus for this. Again we will write the characteristic equation. So you can see this time the characteristic equation will become s square plus 5s plus k equals to 0. It means s square plus s times k plus 5 plus k equals to 0. So you can see this time this equation is basically a quadratic equation. Okay, so it means there are two roots, or you can say the two values of s will be obtained. Okay, so now we will see how the value of s varied as we will increase the value of k from 0 to infinity. So again we will take the value k, 0, 1, 5 and infinity, and basically this is the quadratic equation. So as per Sridharacharya formula, we are having the roots like this. Okay, so minus k plus 5 by 2 plus under root k square plus 6k plus 25 by 2. How we have obtained this? This is from minus b plus minus under root b square minus 4ac upon 2a. This is basically the expression for ax square plus bx plus c equals to 0 type equation. Okay, so we have written this. Then we will put the value of k equals to 0. Then we can see the value of s for k equals 0, s1 equals to 0 and s2 equals to minus 5. For k equals to 1, it is minus 0.17515, it is minus 5.828, and this is, you can say, and for k equals to infinity, this is minus 1, this is minus infinity. So now again we will plot it. Okay, so we will plot it. We can see this is basically the root locus, 0, minus 1, minus 5 and minus infinity. So we can observe number of branches are again 2, that is number of open loop poles. So from here we can see that there are 2 poles. So we are having 2 branches and 1 0 at s equals to minus 1. So what happened? From here we can see this point terminates. This point terminates here. Here there is no root locus. Okay, and this point minus 5 will terminate at infinity. So from this you can see that one pole which was lying at s equals to 0 terminate at a one pole which was lying at s equals 0 terminate at a 0 which is lying at minus 1, and another pole which was lying at minus 5 will terminate towards infinity from here. Okay. So now what is the issue with this particular method? Let us suppose we will work with higher order systems in which characteristic equation is having 6th or 7th order, and you are having 6 or 7 roots, or and you have to calculate all the roots, and so it is a very difficult task to do this. So for that basically some rules were given by the Evans. Okay. So we will see those rules. So it is very difficult to plot the root locus of higher order system by the method actually substituting different values of k in the root of characteristic equation as used above. To simplify the construction of root locus for higher order system, certain rules are specified based on the observation made earlier. Okay, so we will use those rules to get the root locus. Okay. So here there are some particular things, there are some specific rules. Out of those rules, one important thing is breakaway points. So in this particular question, we will see that how we will obtain the breakaway points. Okay, so this is the transfer function given to us, open loop transfer function given to us, k upon s times s plus 1 times s plus 4. Determine the coordinates of valid breakaway point. So valid breakaway point. So first of all, we have to find out the breakaway points. Then we will check validity of those breakaway points. So first we will write the characteristic equation 1 plus gs into hs equals to 0, and then we will obtain the polynomial in S. So you can say this is a third order polynomial. Okay. So for calculating breakaway point, we will first calculate the value of k in terms of S. Then we calculate dk by ds. It means differentiate k with respect to s. Okay. So when we will differentiate it, it will become minus 3s square minus 10s minus 4. Then we will put this value equal to 0. As this is a quadratic equation, so again we are having 2 roots. So we have, when after solving again using Sridharacharya formula, so we are having breakaway points, which is minus 0.46, minus 0.28, minus 2.86. Okay, these are the breakaway points that we have obtained using the quadratic equation. Now we will check the validity. So which one is the valid breakaway point and which one is not the valid breakaway point? This can be obtained. How? We will put this value of S again in this equation, and if the value of in this particular equation, and if the value of k is found to be positive, if the value of we will put the value of breakaway point in this equation of k, and if the value of k is found to be positive, then that particular breakaway point is basically the valid breakaway point. So this is the expression for k. When we will put the value of s equals to minus 0.46 here, k will become plus 0.8793, and when s equals to minus 2.86, k value will become minus 6.064. So you can see for breakaway point s equals to minus 0.46, the value of k comes out to be 0.8793, which is a positive quantity. So this is our valid breakaway point. Okay, and this is not the valid breakaway point. Okay, and basically if we have to see that what happened at the breakaway point. So at breakaway point, what happened, the root when two roots with same gain came at a point, then it will break away. Breakaway means it will break away at an angle of plus minus 180 degree by n, where n is the number of branches approaching at a particular breakaway point. Okay, so here the number of branches are 2. So angle of approaching will become plus minus 90 or plus minus pi by 2. So you can see one root is here, one root is here, it will move here, it will move here, and at this point, this is the valid breakaway point at which one root move in this, one branch move in this direction, another branch move in this particular direction. Okay, and this you can also see from a rule. If you will locate these poles at s equals to 0, at s equals to minus 1, and at s equals to, sorry, here 0 is there, here it is a pole. So according to a rule, there will be sorry, it is at s equals to 0, at s equals to minus 1, and at s equals to minus 4. These are basically the 3 poles for this particular question. So as per a rule, no point on the root locus lie if the number of sum of open loop poles and zeros towards right is even. Okay, so you can see if there is any point in between, you can see the number of sum of open loop poles and zero towards right will become even. So there will be no root locus between this range. There will be no root locus here. Okay, so from here, if there is no root locus, then this breakaway point is always the part of the root locus. So if there is no root locus over here, so minus 2.86 will be lying over here. So it is not a valid breakaway point, because breakaway point will always be the part of root locus, and if root locus does not exist over here, then there is no question of lying breakaway point over here. Okay, this is another question, angle of departure. So angle of departure is basically measured at the complex poles. Okay, so how from the complex pole the branches will leave. Okay, this is about the angle of departure. So how it will be calculated? So this is the open loop transfer function given to us. Okay, from here we can see 1, 2, 3, 4. There are 4 poles, 1, 0. So p equals to 4 and z equals to 1. Poles are lying at s equals to 0, minus 4, and if you will solve it, it is minus 1 plus minus j. Okay, now we will draw the pole 0 plot, and we will obtain the angle of departure at minus 1 plus j. And minus 1 minus j is simply the negative value of this value, minus 1 plus j. Okay, so how we will calculate it? First of all, we will draw the poles and zeros in S plane. So one pole it has s equals to 0, another one is at s equals to minus 4, another one is at minus 1 plus j, and minus 1 minus j, and at s equals to minus 2 there is a 0. So what we will do, we will make line like this from all the poles and zeros to this point and measure the angle. Like this is the first pole, so angle is, let's say, 5p1. This is the second pole, this is 5p2, this is third pole 5p3, and this is 5z1. So we will calculate 5p1, 5p2, 5p3, add them. We will calculate 5z1. So we will calculate all the angles from poles, 5p1 plus 5p2 plus 5p3. and similarly phi z, and we will calculate phi p minus phi z, sigma phi p minus phi z, and the angle that we will obtain we will subtract from 180. Okay, so from here we can see what should be the value of this phi p1. Phi p1 will become, this value is 1, this value is 1, so this value will become 45 degree. So phi p1 is nothing but 135 degree. Simply phi p2, this angle is 90 degree. Phi p3, you can see this distance is 1, and from here this distance is 3. So phi p3 is tan inverse 1 by 3, which comes out to be 18.43 degree. Okay, so we will add it up, all these poles, angles from all these poles, so it will become 243.43. Then phi z, this angle, so this is 1 and this is 1, so this angle is 45 degree. So this is 45 degree. So we will phi p, sigma phi p minus sigma phi z comes out to 198.43. Then we will subtract it from 180. So we are having minus 18.43 degree angle of departure. Okay, minus 18.43 means angle will somewhat like this. You can say this angle is minus 18.43 somewhat here. So it is like this. Okay, and similarly phi d at minus 1 minus j will become 18.43 degree if you calculate angle of departure here. Okay, so this is you can say, if this is your pole, another pole is this, so you can say this angle is basically like this, 18.43 minus, and this is 18.43. So this is basically angle of departure. Now we will see one question based on root locus, complete question. So first of all we will calculate the number of poles, and we will see the number of poles and zeros. So you can see here are 3 poles, so p equals to 3, there is no 0, z equals to 0. So number of branches of root locus is n or p, whichever is greater. So here n equals to p equals to 3. Now we can see there are 3 branches and there is no zeros. So all the branches will originate from open loop poles and terminate towards infinity, because there is no 0. Okay, so poles are at 0, minus 1 plus j and minus 1 minus j, and there will be no breakaway point exists, because if you will see this is the only point lying at negative real axis, and other two are lying here, so there will be no breakaway point. This we can also see. Now we will see the angle of asymptotes, which is 2q plus 1 into 180 upon p minus z. So there are 3 asymptotes. Asymptotes are the points by which the branches of root locus reaches towards the infinity. So from this formula, if we will calculate, we are having values 60, 180 and 300. These 3 are the angle of departures, and these angle of departures starting from centroid, and the centroid value is sigma real part of poles minus sigma real part of zeros upon p minus z. So when you will solve it, this comes out to be minus 0.67. So this is the point from which the angle of asymptotes will meet. Okay, so this is the point, minus 0.6, from which angle of asymptotes meet. Now we will see breakaway point. So as we have already seen that there will be no breakaway point, but we can calculate it analytically also. So we will put 1 plus GSHS equals to 0, and again we will calculate the value of k, then dk by ds. So we are having breakaway points, complex breakaway points, and how we will put this value from here to here, but it is a difficult task. So we suggest angle condition to check the validity of these breakaway points. Okay, so by angle condition, when we have checked it, So we will calculate the angle at these points, and if this angle is a multiple of 180 degree, then we can say this is a valid breakaway point. But we will see their angle is minus 64.11. So these breakaway points are not the valid breakaway points. Okay. Now we'll check the intersection with imaginary axis. So we will put characteristic equation equal to 0. For this, we will use the Routh-Hurwitz criterion, and with the help of Routh-Hurwitz criterion, we calculate the point which is plus minus j 1.414. So this is Routh-Hurwitz criterion for sustained oscillation. This value should be equal to 0. So k marginal equals to 4. We will make the characteristic equation with the help of this. So this value of S will become like this. Now, because there are complex folds, so we have to calculate the angle of departure as I have discussed previously. So angle of departure comes out to be minus 45 degree for minus 1 plus j, and for minus 1 minus j it is plus 45 degree. Okay, now we will draw the complete root locus. Okay, so you can see this is your pole, another pole is here, another pole is here. Okay, 3 asymptotes are coming from this point. Okay, so as there is one asymptote here, so this branch will move towards this direction. Okay, and these two are complex roots, and this will reach towards infinity and meet the imaginary axis at plus minus j 1.414. So this is this point. Okay, and angle of departure we have calculated is plus 45 degree. It means this angle is 45 degree, this angle is minus 45, this is plus 45. Okay, so it will comes out to be like this and like this. Okay, so you can see the k marginal equals to 4. So if the value of gain k will be increased from k equals to 4, then what happened? These two roots will lie towards right half of the S-plane, and your system will become unstable. Okay, but as you will see, increase the value of gain, then this root will moving in negative real axis towards negative real axis, so it will not affect the stability. But for stability, the value of k should be less than 4. For k equals to 4, system will become marginally stable, and k greater than 4, system will become unstable. Okay, thank you.